So, let us see what we have covered so far. So, we started off with the prerequisites for this course. I really want all of you to take this somewhat seriously, because if you do not have prerequisites, you please make an effort to acquire them. So, the other thing we discussed was a historical timeline of notable events and milestones in the development of the subject. The other thing we discussed was the 0th law. We mentioned the 0th law, first law, and we mentioned and discussed to some extent the Clausius and the Kelvin's form of the second law of thermodynamics. Then we also made an effort to prove the equivalence of the Clausius and Kelvin forms of the second law. Then we went on to discuss or explain the nature of or the meaning of microstates and macrostates of a thermodynamic system. Then finally, we ended with the definition or the Boltzmann definition of the entropy of a thermodynamic system. You see that the definition of entropy from the point of view of Boltzmann is it's basically a combinatorial quantity. It's all about counting the number of microstates subject to certain constraints. So, now I want to discuss another facet of entropy that is often mentioned in various courses and other discussions of thermodynamics and statistical mechanics, namely that entropy is a measure of the disorder of the system. So, we really want to understand if that is really true or to what extent is that true. So, I am going to show you a sequence of slides, somewhat amusing, I should admit, that you will see that the notion of disorder is actually somewhat vague and imprecise compared to the definition that Boltzmann gave. Okay, so, let us get on with it. So, the question is entropy a measure of the disorder in the system? So, imagine that there is a lecture on entropy which this lady wants to attend, and then you see the advertisement for the lecture on entropy starts off meaningfully. It starts off by saying, well, this lecture aims to illustrate, and then later on it becomes less and less intelligible, and finally it becomes a whole lot of nonsense. So, the question is, if I ask yourself, can you spot phrases that are ordered and phrases that are disordered to whatever extent and meaning that you can attribute that to? You would probably immediately jump up and say, well, the first few words, the first sentence, the first line makes sense, then after that it makes a little less sense, and later on it makes no sense at all. So, you would kind of instinctively probably think of the first line as being ordered and the later lines as being disordered, or the whole paragraph kind of tends towards chaos. So, however, I want to point out that this is a certain bias that we have, which is called I call it as a bias of coarse graining. Okay. So, let me discuss what I mean by that. So, let me give you a slightly different example, but a similar one. So, it starts off, this lecture aims to illustrate how entropy is a measure of disorder. It is in perfectly grammatical English. But then the very next sentence has the word entropy, but the rest of it does not seem to make any sense. And the third sentence makes no sense at all. It does not have any word that I can relate to. And the fourth one similarly does not have anything. And the fifth one vaguely has a certain word like entropy. So, you see, then if I ask you the same question, you would still probably say that well, this is also a paragraph which is mostly chaotic, except the first sentence which is in red, which is ordered and it makes sense. But then I have to point out to you that this is a bias, because actually each of these sentences say exactly the same thing, but in different languages. So, I can't remember which one is which, but I will tell you, for example, the penultimate sentence is in the South Indian language of Kannada, and the third sentence is in Arabic. It says exactly the same thing, namely, this lecture aims to illustrate how entropy is a measure of disorder. So, it's someone who knows Arabic only and doesn't know any of the other language would in fact call this paragraph chaotic, but the ordered sentence would not be the English sentence, but rather the Arabic sentence, which is the third one. So, it is important for you to understand that what we call as a ordered collection of microstates is actually a human bias. Okay, so let me give you another example. So, this is a vase which is not broken, and on the right you see a vase that is broken. So, now I can ask myself and others, which one is ordered and which one is disordered. You would probably instinctively say that, well, the vase that is not broken is ordered, the one that is broken is disordered. And why would you say that? So, you would probably say that because the number of ways in which you can take a vase that is not broken and break it is infinitely more or enormously more compared to the way in which you can take a broken vase and convert it back to a real vase. So, you see here we are able to see the bias that we are talking about. See what we have labeled as ordered is precisely one set of microstates. It is one microstate. If you like, if you take all the collection of all the pieces as a microstate, then it is precisely one microstate. But the disordered state is a vague notion, because there are too many different ways in which a vase can be broken, and yet we all have decided to lump all those different ways in which a vase can break, and we have called all of that disordered. So, that is the bias that I am talking about. So, instead what we really should probably do is that instead of calling the broken vase disordered, we should really call it ordered of type 1, and this is ordered of type 2, and if you rearrange the pieces that are broken, that would be the ordered of type 3. So, there is no such thing as a disordered phase.
Okay, so as I told you earlier that it is our human bias that makes us think that a broken vase is disordered, whereas a unbroken vase is ordered. So, I just if you recall, I showed you earlier 3 pictures, and I suggested that rather than calling the broken vase as disordered and the unbroken vase as ordered, we should simply call all of them ordered, except they are of different types. So, you can in fact, a similar bias is seen in the next example. Imagine I have a hand of cards that is shown here. So, it starts with ace of spades, and then there is 2 of spades, and so on and so forth. So, it is ace 2, 3, 4, 5, 6 up to a king. So, they are all the complete spade suit. So, now I ask myself, so this is an unshuffled suit. Then suppose I shuffle this hand, what will I get? I will get a shuffled hand. So, let me ask myself this question, which is more likely? Suppose I have a unshuffled hand and I shuffle it, I get a shuffled hand, or is the reverse more likely? I start with an unshuffled hand and I shuffle it, and will I get an ordered hand? So, suppose I ask you that question, you will probably not hesitate in answering that it is more likely for an unshuffled hand to become shuffled rather than the reverse. But then if you pause and think about it, there is nothing, in fact both are equally improbable. See, the reason is because, see, just as this sequence of cards is a unique sequence, you see this particular sequence that I have, which is I have called unshuffled, it is actually also an equally unique sequence. See, there is the first card 3, the second card is 6, and the third card is king. So, this is as unique as this. So, there is nothing unshuffled about this. This is just another way of ordering a set of cards, and so is this. So, as a result, if I ask myself what are the chances that if I start with this sequence and I shuffle my cards that I get exactly this sequence, the chances are extremely unlikely. But then so is the reverse. So, I start with this sequence and I shuffle the cards, the chances that I get back this sequence is equally unlikely. So, in that sense, so what we are doing in statistical mechanics is we are actually coarse graining by saying that this is ordered and anything that does not resemble this sequence is disordered, or so basically we classify them all as shuffled, but it's shuffled is not one sequence of cards, but rather a whole bunch of sequences of cards which are not resembling this sequence. So, in that coarse grain sense, so if you lump a whole bunch of sequences as shuffled, then it becomes fairly obvious that it's overwhelmingly more likely for a unshuffled hand to become shuffled than it is for the reverse to happen, because the unshuffled hand is actually not one sequence of cards but a whole bunch of sequences, and so that way the irreversibility creeps in. So, that is actually the origin of the second law of thermodynamics according to Gibbs.
So, I hope I have made it clear that the idea that entropy is a measure of disorder is only in this sense that we have decided to coarse grain our notion of what a disordered hand is. So, if you lump a whole bunch of states together and choose not to distinguish between them, then it is true that an ordered state will overwhelmingly likely to become an unordered state than it is for the reverse to happen. So, in fact, Gibbs correctly pointed out that it is this bias that makes us believe that entropy of a system, which second law of thermodynamics, which says that the entropy of the system increases with time. So, that is another formulation of second law which I did not discuss till now, but that is the second law of thermodynamics, which says that if you have an isolated system where nothing comes in, nothing goes out, and you look at the entropy of that system, it either does not change with time or it increases with time. So, the reason for that according to Gibbs is because we choose to define entropy in this coarse grained sense. So, we choose to purposely ignore the subtle variations of the microstates between different possibilities, and we lump all of them as a huge class, as a disordered state, and we do not care about anything else. So, let me get to this some calculations of let us try to learn how to get some numbers out, actually calculate entropy as a number. So, you know that Boltzmann explained to us that entropy is nothing but the logarithm of the number of microstates subject to a certain constraint. So, now here is a deck of a hand of playing cards. So, now you know that a standard deck has two colors, black and red, and there are 26 distinct cards of each color. So, imagine I have a hand that has n cards, and now imagine that that hand has n1 black cards and the rest are red cards. So, n minus n1 red cards and n1 black cards. So, now I can ask myself if there is a standard deck sitting on my table and I pick cards one by one, what are the chances that I will end up with a hand that has n1 black cards and n minus n1 red cards? So, the answer is clearly it is a simple combinatorial problem, and it is just the the binomial coefficient, or the 26 choose n1, which is the number of ways in which n1 black cards can end up in your hand, and 26 choose n minus n1 is the number of ways in which the remaining cards can end up in your hand. So, now the entropy of the system, so the overall number of ways this can happen is really the product of these two numbers. And now, according to Boltzmann, the entropy of the system is the logarithm of this overall number of ways in which you can get this hand. from a standard deck of cards. So, as you can see, I have written the formula here. The entropy is the logarithm of the product of these two numbers. So, now what I am going to do is I want to plot. So, before I plot, let me point out what are the microstates and what are the macrostates. So, actually the microstates have been subsumed in the combinatorics. So, that means I have a huge number of microstates which lead to this huge combinatorial number like C26N1. So, that it is all hidden there. But then what are the macrostates? The macrostates are these two numbers N and N1. So, the macro state is described by this collection of two numbers. One is the total number of cards, the other is the number of black cards. So, by implication the number of red cards is the difference between the two. So, now you can see that each macro state really corresponds to a huge number of microstates. So, now let me plot this entropy versus the number of black cards. So, suppose I have 10 cards in my hand and I can plot the number of the entropy which I have previously defined, and you can see that it starts off being small. The entropy is not 0, but it's it's not 0. If the entropy is 0, it means there should be precisely one way of achieving that hand. So, but we know that even if you have no black cards at all, so if all the cards in your hand are red, there are still many ways in which you can get that hand, because after all there are only 10 cards, 10 red cards in your hand, but your deck has 26 red cards. So, obviously there are still many ways in which you can get that hand. So, even if you start off with no black cards at all, which is the origin of this plot, so you will still have an appreciable entropy, and as you increase the number of black cards, the entropy goes up and it reaches a peak, and then it comes down, and when you have only black cards in your hand, it again becomes the same as what it was when you have no black cards in your hand. So, this is very characteristic of systems where there is a limit to how many cards there are, or there's how many energy levels there are. For example, later on we will see that if there is an upper limit to the microstates that you are looking at, then it is always the norm that the entropy initially increases, then comes down. So, in fact, one can define, later on we will see that there is something called the temperature of the system that one can define, and here also we may define the temperature as basically the reciprocal of the slope of this plot. So, if you make this plot and find the slope and plot the reciprocal versus the number of black cards, you can see that the temperature of the system initially is positive. Then when the number of black cards is equal to the number of red cards, the entropy, the temperature rather, goes to 0, and then it becomes negative. So, in fact, you shouldn't be alarmed by negative temperature, because negative temperature is simply a symptom of the system not having enough microstates at the upper end of the spectrum. So, that means as you increase the number of say the black cards in this example, that you run out of states. You do not run out of it fully, but then you will run out of it quite rapidly, and which explains the reason why temperature again or the entropy comes down, and as a result the slope is negative, which makes the temperature negative. So, now let me get to another example which is also illustrative of the notion of entropy and also temperature, and that is the example of a staircase, where imagine that there are n1 people standing on a staircase, and imagine that staircase has say m steps, capital M steps. So, imagine a microstate where there are a small n1 people, and notice that people are all different individuals. So, they are all they have different names, different genders, they are all different people. So, they are all standing on different steps, and there is no restriction, let us assume that how many people can stand on a step. So, imagine that it is a very wide staircase, there is no there is plenty of room. So, anyone as many people as you want can stand on a step. So now imagine that there are n1 people standing on the first step, n2 people standing on the second step until you reach the last step. So now the total number of people on the staircase therefore is the sum of n1, n2, n3 and so on up to nm, and that is constrained to be equal to n. So let us assume that the total number of people is fixed. So nobody enters and or exits that hall where the staircase is present. So you only have a fixed number of people and they are all standing on the staircase. So now you can ask yourself, what is the potential energy of this microstate? So imagine that all the steps are of equal height and all the people, each of the persons have the same weight. So this is just for simplicity. So as a result, each person contributes Wh to the potential energy, if they are standing on the first step, for example. So now the total potential energy of the system is the number of people standing on the first step, which is n1, times the potential energy of the first step, which is W into H. So again, then you have to add that to the number of people standing on the second step, which is n2, and you have to multiply that with the potential energy of the second step, which is twice Wh, and so on and so forth until you reach the last step. So notice that we have assumed that there is a last step. That means that the total number of steps is fixed. So in fact, this is going to lead to a behavior similar to the behavior we saw earlier in this example with a deck of cards. So you will see that the entropy increases and then comes down. So we expect similar behavior in this staircase example, simply because the total number of steps is fixed. So later on we will see an example where this is not the case and infinitely many steps. Right now let us assume that there are finitely many steps, which is capital M, and let me ask myself, how many ways are there of redistributing these n different people on these m steps such that their total potential energy is U. So now so what we have to do really is solve these this mathematical question, namely solve this equation. So we should be able to solve the equation n plus n2 plus nm equals n. Okay, so now let us get to the next example, which is that of a staircase. So imagine that there is a staircase on which there are several people standing. So I am going to assume that the people are all different individuals. So each person is different, they are different genders, they have different names and so on. But let us assume they are all weigh the same for this example. So let us assume that there are capital M number of steps and each step has the same height. So now I am going to ask myself, I am going to describe a microstate where there are n1 people standing on the first step and n2 people standing on the second step and so on until the mth step, so until the last m step. So of course, by implication we will assume that there is no there is plenty of room on each step. So there is no restriction on how many people can stand on each step. So now however, the restriction that finally emerges is that because the total number of people is fixed, which is capital N. So I have to make sure that the microstate that I am looking at, which is described by these numbers n1, n2, n3 up to nm. So they have to have the property that if I add them all up, I should get the total number of people on all the steps put together. Now I can ask myself, I have a further constraint rather, that is I am going to demand that not only should the number of people be fixed, I also demand that their potential energy put together should be U, which is fixed. So now you see, let me count the potential energy of this combined system of people standing on the staircase. So now you see, n1 is the number of people standing on the first step, and on the first step the potential energy is W times H, and W is the weight of each person and H is the height of each step, which we will assume is common to all the steps. So, all steps are of the same height H. So, now N1 times W H is the potential energy of people standing on the first step, and the potential energy of people standing on the second step is N2 times 2 W H, because the potential energy of the second step is 2 W H. And the potential energy of the last step is m W H, and the number of people standing on the last step is N m. So, that is this equation that I am talking about. So, you see I have now two equations and several unknowns, and these are all my unknowns, and I have to obviously there are too many unknowns and too few equations. So, obviously I will get a huge number of solutions. But then the only restriction now is that N1, N2, N3 and so on are all integers and they are greater than or equal to 0. So, now in principle I have to list all the possible solutions of these two equations, and then I count how many solutions there are, and that will be the total number of microstates. And according to Boltzmann, if I take the logarithm of that quantity of that number, what I get is basically the entropy of the system. So, now these two equations are actually a special case of what are called Diophantine equations, which is named after a Greek mathematician who lived in antiquity. But then I have to point out that well before Diophantus, a special case of this equation with two unknowns N1 and N2, where epsilon 1, epsilon 2 and u being integers. So, all these are integers, and positive, and there is a method for solving this in terms of the unknowns N1 and N2 given epsilon 1, epsilon 2 and u, and this was invented by Aryabhatta in the 4th to 5th century. And this method was later explained properly by his successor Bhaskaracharya, who lived in 600 AD and 680 AD. So, this is just I just want to point this out, because the algorithms were actually first invented long before Diophantus himself wrote down his equation in a general way. And the special case of Diophantine equation, namely the one that I am staring at right now, these two, they are actually called Frobenius equations. So, they are a special case of Diophantine equation, and you should not confuse that with the Frobenius method of solving ordinary differential equations with non-constant coefficients. Okay, so, a not so good way of solving these Diophantine equations or Frobenius equations is to list all the solutions of these equations and then count how many they are, and take the logarithm and you get the entropy. And if you really want to do it this way, there are codes available in languages such as Python, Mathematica and so on that can do this. But later on we will see in this course that it is not really necessary to list all the solutions, rather you can count the number of solutions without actually listing them, and there is an analytical method for doing this, which I am going to describe subsequently, and that is called the generating function method. But however, coming back to the wasteful way of doing it, so if the number of people on the steps are small and the number of steps are also small, so as a result the potential energy is small. So, we can actually without much effort list all the possible solutions of these two Frobenius equations and then take the logarithm and get the entropy. And so, that can be done by hand, and that is something probably in some of the exercises I will be encouraging you to do that by asking you to repeat this calculation for 5 steps and 6 people and that sort of thing. Okay, so now let us take a specific example with 2 steps and 3 people. So now you see the constraint that I have is that the number of people is 3 and the number of steps is 2, which is described by this index there. So, there are 2 steps and 3 people. So, what are the ways in which I can manage this? So, you see, all 3 people can be on the first step, or 1 person can be on the first step and 2 can be on the second, or 2 can be on the first step and 1 can be on the second step, or all 3 can be on the second step. So, these are the only possibilities. But notice that the people are all different, so it is going to also affect the way in which we count. So, in the first case, the potential energy is when all people are all the people means there are only 3 people, they are all standing on the first step, the potential energy is 3 Wh. Now, in the second case, the potential energy is Wh, because there is only 1 person standing on the first step and there are 2 people standing on the second step. So, that means 2 people 2 times the potential energy of the second step, which is 2 Wh, which is 5 Wh. So, similarly, if you look at the third case, in the third case there are 2 people standing on the first step and 1 person standing on the second step. So, it is 2 times Wh for the first step and 1 times 2 Wh for the second step, and that makes it 4 Wh for the third case. And the final case is when the potential energy is such that all the people are, or all the people means that all the 3 people there, they are all standing on the second step. So, in which case the potential energy is 3 people times the potential energy of the second step, which is 2 Wh. So, you can write a list plot or a point plot of the entropy, because entropy is now a very discrete object, because there are so few people and so few steps. So, you see, so if the energy of the system is Wh. So, I am just thinking of a simple example. So, if I have taken Wh to be 1 actually. So, if when Wh is 1, so what are the possibilities for the energy? You can see that the smallest possible energy is really 3. So, and the largest possible energy is 6. So, it is the values of u on the x axis are going to be 3, 5, 4 and 6, or rather 3, 4, 5 and 6. So, on the x axis you have only these possibilities 3, 4, 5 and 6, and on the y axis you have the entropy, which is the logarithm of the number of ways in which the energy can be 3, 4, 5 and 6. So, let us see how many ways there are in which the energy can be 3. So, when can you get 3 Wh as the energy? That is when all the people are standing on the first step, all 3 people are standing on the first step. So, there is only one way in which you can do that. You just simply make all 3 people stand on the first step. But however, in the second case, there is 1 person standing on the first step and 2 people standing on the second step, and there are 3 ways of doing this, because notice that the people are all different. So, you can make George stand on the first step, Aditya stand on the second step, and Saurabh stand on the second step. So, you have 3 people, but still then you can interchange, you can make Saurabh stand on the first step and George stand on the second step, you get a different configuration. So, because the people are all different, so there you get different ways of doing that, different ways of achieving the potential energy 5 Wh. And how many ways there are of doing this? Clearly, there are 3 ways of doing it, because you just have to decide who stands on the first step, and then the other 2 are forced to stand on the second step. So, same in the case of the third example, where you force 1 person to stand on the second step and the other 2 are forced to stand on the first step. So, that 3 ways in which you can select the person you want to make stand on the second step. So, as a result, when the potential energy is 4 or 5, the number of ways of doing it is 3. So, the entropy is log 3 in these 2 examples. So, as a result, you see the entropy is 0, because there is only one way of doing it when the energy is 3, and there is only one way of doing it when the energy is 6. but there are 3 ways of doing it when the energy is 4 or 5. So, as a result, the entropy is log 3 there, and 0 here and 0 there. So, you see, as a result, even here the entropy increases, then flattens out, then again decreases and becomes 0. So, this is reminiscent of what we saw earlier, namely in this example, in the playing cards example, it has a similar feature. So, now let me give you a slightly different staircase example. Instead of people, imagine there are identical marbles. So, in other words, the people were all different, you had George, you had Aditya, you had Saurabh, they are all different people. But then imagine there are identical marbles. So, when there are marbles, the countings are going to be different because they are all identical. So, here is a typical microstate that I am looking at. So, you have one marble on the first step and then 2 marbles absolutely identical on the second step, and 1 marble on the third step and 3 marbles on the fourth step, and so on. So, in this example, for the sake of being concrete, let me take 3 marbles and 3 steps. So, what are the constraints that I am looking at? I am looking at this constraint that the total number of people, the number of persons should be 3. So, the number of persons is 3. So, n1 plus n2 plus n3 should be 3. But I also want the total potential energy of the system to be fixed, which is U. So, how do I achieve that? I have 3 steps. So, the first step has potential energy WH, so and then n1 people there, which is my microstate, n1, n2, n3 is my microstate. So, you have WH into n1 is the potential energy of the first step, then 2 WH is the potential energy of the second step, and the n2 people there, and 3 WH is the potential in the third step, and n3 number of persons on the third step. And here too I can count the way I counted, and here too you will find that when the energy is either 3 or 4, that the number of ways in which you can do that is just precisely 1, in which case the entropy is actually 0. So, however, when it is 5, 6 or 7, you can figure out what it is. It is going to be substantial, but certainly not. Notice that it is different from the. So, this plot is not exactly the same as the people example. So, here the more energies where the entropy is actually 0. But here too, you see even though it is slightly different because the marbles are all identical, unlike the other example where the people are all different, but here too there is a common feature, namely the entropy actually increases, flattens out, then again decreases. So, here you see that here too the temperature is actually positive for some of the values of u, and then again negative for some other values of u. And this is a symptom, as I said, of a system where the number of steps or the number of energy levels or whatever you want to call it, when that is fixed. So, when you have some restriction, when there is no room at the top, as it were, when it becomes crowded at the top, then the entropy goes down, because you can't really, the number of ways in which you can do things starts to diminish, and you do not have many options left, and as a result the entropy shrinks to 0 finally. So, however, if you do not like that situation and you do not want the entropy to shrink to 0, there is a way of doing this, and that is you do not restrict the number of steps. So, what you say is that I have an endless staircase. Of course, I have a fixed number of marbles or fixed number of people, but I do not restrict on how high they can stand. So, I have an endless staircase. So, now I am asking myself that imagine that I have 10 people on an endless staircase. Well, in this example I have chosen marbles rather than people, because it is easier to do it with marbles because I don't have to distinguish between them. So, I am talking about marbles now. So, you have 10 marbles on an endless staircase, and as by now you should know how to write down these constraint equations, the Frobenius equations as it were. And the first Frobenius equations is the total number of particles, which is forced to be 10. And the total potential energy, and I won't repeat the arguments here, it's going to be U. So, again you can write a code for this. I think you should do it yourself because I don't want to be biased towards any particular language. I prefer a language called Mathematica, which is very nice for this sort of thing, but I'm not recommending any particular programming language. You could work in Python or MATLAB, they are all equally good. But whatever it is, you could simply go ahead and try and solve these equations, and when you do, you get this plot. So, you can plot the number of the energy of the system versus the entropy of the system. So, you see the entropy actually increases monotonically, it never goes down, like it increases with energy. Okay. So, now you can plot the temperature, which is defined as the reciprocal of the slope of the earlier plot. So, it is going to look like this, and notice that it is always positive. So, the temperature is increasing and positive always. So, indicating that the entropy is a non-decreasing function of energy. So, that is a symptomatic of a system where there is no upper bound to the total number of energy levels, or there is no upper bound to the energy of the system itself. So, if there is no upper bound to the energy, there is no crowding at the top, and there is a lot of room at the top. So, entropy can you can rearrange the microstates to get a entropy which is a non-decreasing function of the energy. So, let me now give a name to the objects that I have been calling marbles. So, notice that the marbles are actually indistinguishable objects, and indistinguishability is a hallmark of quantum mechanics. So, you do not have indistinguishability in classical physics because you can always. So, if you have a particle, a classical particle moving, you can always tell it apart from the others, because you can you can know the position and momentum of each particle separately. In principle, you can know what it is, and you can follow each particle around, and so there is no way in which you can confuse that particle with some other particle, because no two particles can be not only in the same position, but have the same momentum. If two different classical particles have the same momentum and same position, they had better be the same particles. So, however, in quantum mechanics, you can't really do that, because you can either track the position or you can track the momentum. So, if you decide to track the position, then you can't be sure that you are looking at the same particle, because you can have another particle with the same position but different momentum, but then you will confuse that for the same particle because they have the same position. So, so the point is that indistinguishability is a hallmark of quantum mechanics. Now, indistinguishable particles in quantum mechanics come in two types. One of them are called fermions, the other are called bosons. So, the example of identical marbles that I gave you earlier, where there is no restriction on how many particles there can be on each step of the staircase, is an example of bosons. So, you can have another example of fermions where there is a restriction, namely you say that I only allow a maximum of one marble on each staircase. So, either I leave that step empty, or I allow only one marble to occupy that step of the staircase. So, in which case you have a total number of, so now your Frobenius equations become this, which is of course the constraint that the total number of marbles is 10, And the second one is, as usual, the total potential energy is U, and the important constraint which tells you that these are fermions is that the number of marbles on each step is either 0 or 1. So, that is a lot to swallow. So, in this hour we have learned a lot, hopefully, but one common thread among all the ideas that you have learned in the last 1 hour is that you have these Frobenius equations that you are forced to solve by hand, and you are forced to enumerate all the solutions rather wastefully just to count how many there are. So, Boltzmann tells you that if you somehow by hook or crook know the number of solutions of these Frobenius equations, the logarithm of that number is the entropy. So, if you are only interested in entropy, it is quite wasteful to list all the solutions, but in this last 1 hour we have done just that. We have used a simple example with a small number of particles, small number of steps, and then we have decided to explicitly enumerate all the solutions and count them explicitly. So, in the next lecture I am going to tell you a very clever analytical way of sidestepping or avoiding having to list all the solutions of these Frobenius equations. So, there is an analytical way, a clever one, of counting how many solutions there are without actually listing all the solutions. That is called the generating function method, and that will be the subject of the next hour of lectures.